3 videos you are currently watching were rendered. But not just with any traditional 3D software, or at least not directly. Each frame in those videos were rendered by an AI. Here, I purposefully use the word rendered, as this was not made using a generative AI model such as Stable Diffusion or DALL-E. No, these are NURFs. NURF stands for Neural Radiance Fields. It's a recent method introduced in 2020 with this paper to learn a 3D environment from photographs, renders, or any images. This then allows you to render any viewpoint in your 3D environment without ever having seen the specific viewpoint before. In this video, I will show you how to use BlenderNURF. BlenderNURF is a Blender plugin that I developed over the last year to create your own NURF datasets directly from Blender within a single click. Now you might be wondering, what are the use cases? If I already have a scene in 3D, can't I just render any viewpoint from Blender directly? Well, yes, but there are other reasons why you might still care about creating your own NURFs. You might be a VFX artist and want to combine some real-world footage with 3D. Or you might care about speed. Rendering can be a slow and compute-expensive process, especially when path tracing scenes with complex materials, lighting effects, or volumetrics. This can take up to hours for a single frame. Or perhaps you're a researcher investigating 3D reconstruction algorithms, and having synthetic data to evaluate your method against can be quite useful. NURFs can nowadays be trained in a matter of minutes or even seconds, and rendering any viewpoint from a trained NURF is even faster. I will split this tutorial in 2 parts. In the first part, I will demonstrate BlenderNURF and show you how to use it to create your own NURF datasets. All you need for this is Blender 3.0 or above. If you're also interested in learning how to train your own NURF, I will exactly do this in the second part using InstantNGP. InstantNGP is a very popular and fast open source NURF software developed by NVIDIA. I will run it on Google Colab, a service for executing Python code with free access to computing resources, including GPUs. Not everyone might have access to an NVIDIA GPU, and that is why I will use Colab instead. Before starting with BlenderNURF, I first want to clarify a bit what NURFs are and what they need. If you are already familiar with the terminology and the concepts, feel free to skip ahead. As I said before, NURFs try to learn a 3D environment from images. They essentially simulate real-world light behavior, or path tracers, by learning the appearance of the 3D environments into a neural network. The word appearance here is important, because NURFs do not only reconstruct the 3D geometry, but also learn reflections and other view-dependent lighting effects. For this, the model needs images of course, but also the camera focal length alongside its position and orientation, or for short, the camera poses. In Blender, extracting this camera information can be quite challenging, and that is exactly what the plugin is for. A NURF dataset therefore consists at least of 2 things: a set of training images and the corresponding camera poses for each individual image. All the camera information is typically stored into a transforms_train.json file. Datasets sometimes also consist of testing camera poses, typically the view angles at which we want to render and evaluate the NURF. You might also need the ground truth test images, or the real test images, but the plugin does not render these explicitly. We only want to train on NURF and render unseen viewpoints. The first thing you will want to do is install BlenderNURF. For that, you can visit this page on GitHub, the link will be in the description, and download the code as a zip file. You can then open Blender, go to Edit, Preferences, and under the Add-ons tab, click Install. Here, select the downloaded zip file, enable the add-on by ticking the box, and you are good to go. The add-on panel and all its functionalities are accessible under the right sidebar when pressing N in the BlenderNURF section. Here, you will see 4 windows, 3 of which are closed and correspond to the BlenderNURF methods to capture datasets, and the top one being the shared user interface. I will discuss each of the methods in more details with their own example files in a minute. For now, let's focus on the shared user interface. You will first notice a few toggle buttons and controllable properties, most importantly the train and test toggles. With them selected, you will respectively export the camera poses for the corresponding training and testing cameras. As you will see, these might be the same depending on the method and your settings. Training a NURF requires training renders, but you can also choose to disable rendering by unticking the Render Frames checkbox. Test images, on the other hand, will not be rendered by the add-on. If you really need them, you can just get them directly with Blender under Render Animation after having selected the test camera of interest. The AABB property is unique to Instant NGP and describes the side length of the bounding volume in which camera rays will be traced during training of the nerve. AABB stands for Axis Aligned Bounding Box and essentially represents a region in your scene that you want to capture. You will want it to keep it as low as possible while being sure that everything in your scene fits within this volume, including the cameras. Larger bounding boxes will, in fact, slow down training and rendering. You can visualize the box by creating a cube centered at the origin and uniform scale equal to the AABB length. If I have an AABB length of 4, the scale of my cube in X, Y, and Z should also be 4. Instant NGP restricts the bounding volume to have a side length equal to a power of 2. That is 1, 2, 4, 8, etc. all the way up to 128. Now, if you do not want to export your camera poses in the Instant NGP format, you can simply toggle the NERF file format. The NGP format will just export more information on your camera focal length, sometimes useful if you plan on rendering your scene with non-uniform aspect ratios. But most of the time, the file format should not matter too much. If the Save Log File checkbox is ticked, you will additionally export a text file for reproducibility. It will contain information on the add-on version, which method was used, and how the properties were set. Finally, the Save Path property is quite self-explanatory and defines a location on your computer under which the dataset will be saved. Now that we have seen the shared user interface, let's explore how to actually render and export a NERF dataset using one of the three methods. I will start with the camera on sphere method, as it is the most straightforward one and the one that requires the least amount of effort. The idea is to randomly place cameras looking towards a particular center of attention. In this way, we can hope to get as good as possible of a coverage in the renders of our scene for the 3D NERF reconstruction. The cameras are randomly placed on a sphere that is controllable with the COS panel. Let's have a look at this via a simple scene with a donut that you might recognize from the Blender Guru tutorials. In this scene, I have a simple camera animation that spins around my donut for 200 frames. But perhaps we could render half or even less frames and instead render out 200 frames using a NERF. The first property is a camera that I want to evaluate or test my NERF on. This is a current active camera, for which I will get the transforms_test.json file exporting the camera poses for all the frames in my scene, given of course that my test toggle on top is enabled. The next few properties give control over the sphere from which the training camera will be sampled. By default, the sphere will be centered at the origin with 0 rotation, scale 1 and a radius equal to 4 meters. The radius is strictly speaking not necessary, but allows for quick uniform control over the sphere size in all 3 axes. Note that the sphere is not directly visible, unless a corresponding preview toggle is turned on. When done so, Blender NERF will create an empty sphere called Blender NERF Sphere, which can directly be controlled like any other object in Blender. If you delete it, you can simply enable it again in the preview, and a new sphere with the same name and the same settings will be created. In this case here, I already adapted the sphere location, scale and radius to best match my scene. The lens property controls the focal length of the camera sampled from the sphere for training. If you want to have a preview of the camera view, you can toggle the corresponding button and select the created Blender NERF camera as active camera. Be careful that when selected as active camera, it will also act as testing camera for the COS method. The seed controls the randomicity of the camera placement on the sphere, useful for reproducibility. In some situations like this one, only the top views of the hemisphere are of interest to our NERF reconstruction. The upper views property comes handy in this case and restricts the camera to only be sampled from the upper hemisphere. This functionality is rotation variant. As the name suggests, the outwards toggle flips the view direction of the camera towards the outside of the sphere. This can be useful when dealing with large scenes such as rooms or landscapes or any other scene without a single center of attention. I will keep it off for now. Finally, before rendering, we can check that our scene fits within an appropriate AABB bounding volume. Here, I created a wire-framed cube with length 4. A smaller cube with side length 2 would not contain the training cameras and would thus be too small for instant NGP. For this scenario, I would like to render 80 training frames on the sphere. In other words, the training data will be rendered on frames 1 up to 80, and the test file will in turn contain the camera poses for all the frames in my scene. Let's play the COS operator and export all the data. This is now rendering my 80 frames, and the camera information for both training and testing has already instantly been created. I can however interrupt the process since I already ran this operator once. The final dataset then looks like this, with all the training images in the train folder and all the camera data stored into the transforms. Let's now move on to the next method. This method and the next one are more specialized use cases, designed to create NeRF datasets or custom animated camera paths. The subset of frames method renders every nth frame of a given camera path and creates a testing path for all the frames. This yields a NeRF specifically crafted for this one camera, in some sense interpolating the images between the training frames of that same path. Again, I've loaded a scene which you might also recognize, since it is a Blender splash screen for version 3.5, available for download on the official Blender website. Thanks to Nicole Morena, the author of this lovely scene. For our purpose, I have animated a simple camera trajectory for 200 frames, in which the camera slowly moves forward with a slight progressive tilt. The subset of frames method now allows me to choose a frame step, here I chose 4, and a camera from which I will export the data. The camera here is again the currently active camera, so be careful to have your correct camera selected at runtime. If I now press play SOF, I will render every 4th frame of my camera animation and create the corresponding testing transforms file containing all 200 frames. And that's it, it's that easy. Let us quickly look at the exported data. And as you can notice, I successfully rendered every 4th frame and have the corresponding camera poses. At last, the train and test cameras method. As the name suggests, this method separates data for training and testing by extracting camera poses from 2 distinct cameras. This becomes handy when you already rendered an animation but consider slightly adjusting the camera path. Instead of rendering everything again in Blender, you can use the already rendered frames as training and render the new camera path with a NeRF. Be careful, however, to ensure that the test views from your adjusted camera do not deviate too much from the training views, since your NeRF cannot invent new information. For training, data will be rendered and exported from a dedicated custom training camera that you can freely select. The testing camera poses will, in analogy, be extracted from a selected testing camera. The scene I loaded here is a classroom demo file provided by Blender, again available on their website. It contains quite a few complex materials and multiple lights, which significantly impacts rendering time. On my hardware, it took me around 6 hours for this simple animation with 100 frames. But let's say I'd like to double my frame rate, or instead render twice as many frames and slightly change my camera animation to include some kind of endless looping spin effect. I could then select my first camera as Train Cam and my new camera as Test Cam. Here, for simplicity, I call them Train and Test Camera. I can then select 100 frames for training and disable the Render Frames button, since I already rendered these 100 frames with the Train camera. Once we place the TTC operator, we instantly obtain the camera transforms files for training and testing, and I can then manually copy my frames over into a train folder. We have just seen how to render and export a NeRF dataset using 3 different methods. The COS method provides a simple and elegant way of obtaining training data without any pre-required camera, while the SOF and TTC methods focus on getting camera data from existing camera paths. Let me now give you a few helpful notes before moving to the second part of the tutorial. Blender NeRF will render everything from the compositor. You are therefore not restricted to the raw render result and can export any kind of data, including normal maps or depth maps. NeRFs will typically start to behave well from 50 to 150 images. Everything in that range should lead to good reconstruction quality. Note that more images do not necessarily mean better reconstruction. From practice, I have also noticed that extreme focal lengths tend to perform worse. Any values between 30mm and 70mm usually work fine for me. And last, for reasons that I am still uncertain of, the vertical camera sensor fit occasionally leads to somewhat distorted nerve volumes. You might want to avoid it if you can. Moving on to the second part of the tutorial, I will now demonstrate how to train a nerve using Google Colab. If you possess an NVIDIA GPU at home, you can directly install Instant NGP on your local machine by following the steps on the GitHub page or by following a tutorial. This will give you access to a more user-friendly interface in which you can just drag and drop your training data. But for anyone else, or if you're just interested, you can just follow along and run Instant NGP on Colab. For this, you will want to visit this link, it will be linked in the description, and log in with your Google account if not already. I specifically tailored this code for BlenderNerve, and therefore all you need to do is run some code cells and input a few parameters. Let's first install Instant NGP by running this code section. This will take a few minutes, enough time to grab yourself a coffee. Once done, you can then have a look at which CPU was assigned to you. Here, I got a Tesla T4. On the side, you will also see that an Instant NGP folder was successfully created. The next step involves uploading and preparing your data. You can either upload your BlenderNerve zip dataset directly to the Colab drive or access your Google Drive. I would recommend using Google Drive, as uploading and downloading data is much faster there. Here I input the path to my data. Let's select the COS dataset stored on my Google Drive under public BlenderNerve dataset cos.zip. I can then just run the next code cells as they are. They will ask me for permission to access my Google Drive and adapt the folder structure to best fit Instant NGP. My data is now split into train data and test data folders. For training and rendering, I will slightly reduce the resolution to 1400 by 600 pixels in order to speed up things, instead of the default resolution of my renders, which was 2100 by 900. If you want the default image resolution, just leave the width and height unchanged at 0. And instead of training for 2000 iterations, I'll train for a bit longer, let's say 5000 iterations. Finally, all there is left to do is to run this cell, which will train my nerve and render the frames for my test camera path. After a few minutes, everything is stored under my test data folder in the test subfolder. The last code cell gives me the option to compress and save my test frames to Google Drive. And here's my animation once I downloaded the frames from Google Drive and stitched them together. It is worth noting that neural radiance fields are barely 2 years old and are still undergoing a lot of research and development to improve on the existing flaws. The two main limitations are the following. 1. Nerves only work on static scenes. This means that you cannot have moving objects in your 3D environment other than cameras. And 2. Nerves also require quite a bit of training data alongside accurate camera poses. There is oftentimes a trade-off between training time, rendering time, and the quality of your trained nerve, which will depend on the size and resolution of your dataset. Also, keep in mind that the nerve training and rendering speed will, of course, also highly depend on your hardware. In some cases, it might just make sense to render each individual frame in Blender directly. With radiance fields becoming the standard in 3D reconstruction applications, I can imagine a near future in which 3D software might directly ship with some kind of nerve engines. Luma AI, for instance, is already extending their services for integration into Unreal Engine, and other developers are similarly following with native support in Blender. In the meanwhile, a lot of research is going into the making of controllable and dynamic nerves. For those that are interested, I will leave a few related links in the description. If you made it so far, well, first of all, thank you. I will make BlenderNerve also available on Blender Market, and if you like my work, you can support me there by buying me a coffee. Of course, feel free to like, comment or share this video, and with this, I wish you a great day and a lot of fun nerfing your scenes in Blender.